Variation of parameters is a method for finding a particular solution to a non-homogeneous differential equation. Furthermore, in our class, we've focused in and we are using variation of parameters only for second order non-homogeneous differential equations. And in order to use variation of parameters, we need to start off with the differential equation in what we think of as this standard form. And when you are in standard form, g of x is going to be the non-homogeneous part when that leading coefficient is 1. So if you start off with a leading coefficient of something other than 1, your first step is going to be to divide everything by it. In order to use variation of parameters, you need to begin with a general solution of that corresponding homogeneous equation. That is, you need these two linearly independent solutions, y1 and y2. With that in mind, variation of parameters tells us the following: that a particular solution, y sub p, is going to have this form u1y1 plus u2y2, where these integrals define u1 and u2. Note, in the integrals, g of x, once again, is the non-homogeneous part of the differential equation when you are in standard form. And the Wronskian y1 and y2 must be non-zero because your y1 and y2 are linearly independent solutions. So let's go ahead and work through a specific example. In this example, we are asked to find a particular solution of this differential equation. In terms of classifying, note it's second order. It's non-homogeneous because of this e to the minus t natural log of t. Classifying it a bit further, note the homogeneous part does have constant coefficients, but our non-homogeneous part, this e to the minus t natural log of t, this is not one of these so-called nice functions that we discussed previously. What that indicates to us is even though it's a constant coefficient, we cannot use undetermined coefficients. The only choice for that particular solution is we must use variation of parameters. In order to use variation of parameters, we start off with finding y sub c, regardless of whether we are asked to find a particular solution or the general solution. So to find y sub c, we solve y double prime plus 2y prime plus y equals 0. Second order, homogeneous, constant coefficients. Kind of the ideal scenario. The auxiliary equation is r squared plus 2r plus 1 equals 0. That factors very nicely. So we have r1 and r2, our roots, are both minus 1. The general solution, and note our independent variable is t, so our general solution is going to be c1 e to the minus t plus c2, and then we have an extra t for that repetition of the root. And before going on to use variation of parameters and find our particular solution, we first need a few key ingredients that I usually calculate beforehand. So we need to indicate what function is going to play the role of y1 and what function is going to play the role of y2. So in this case, y1, and you could choose either or here, will it be e to the minus t? And y2 would be that second function, t e to the minus t. I will let you all do the computation to find the Wronskian, but this is an example we've worked through previously, and in this case it's e to the minus 2t. And then it's also worth noting what function is playing the role of g of t. We are in standard form, so it's simply the non-homogeneous part. So our g of t in this case is the e to the minus t natural log of t. Putting this all together, our particular solution is going to be u1 multiplied by y1 plus u2 multiplied by y2, where in this case we have integrals for u1 and u2. So u1 is going to be minus the integral of y2 multiplied by g of t, all divided by the Wronskian. And u2 is going to have a similar format. It's going to be the positive, in this case, integral of y1 multiplied by g divided by the Wronskian. And note in this case, because I'm trying to illustrate the method of variation of parameters, I'm not going to go through all of the details with the integrals, but I will note they actually work out much better than maybe expected by first glance. So all of the exponentials cancel, and we're left integrating t natural log of t. So one application of integration by parts would allow you to get this integral as minus 1/2 t squared natural log of t plus 1/4 t squared. And recall with variation of parameters, u1 and u2, these are scenarios where we do not want to include a plus c. Similarly with u2, one application of integration by parts, once we realize all those exponentials cancel, will give us t natural log of t minus t. And once we've evaluated these integrals, we can now combine everything together to write down our particular solution. So our particular solution in this case is going to be u1 multiplied by e to the minus t plus u2 multiplied by te to the minus t. And of course there's a few terms that we could kind of combine together and simplify, but I am perfectly fine with leaving your solution in the form that we see here. And let me finish with just a quick observation. For finding particular solutions, we have two methods: undetermined coefficients, variation of parameters. They both apply in fairly specific scenarios in terms of what's required in order to use them. So make sure you are familiar with that, and make sure you can quickly and efficiently determine which method will apply to a given differential equation.